All right, so let's go ahead and dig into our new unit. All right, fundamentally, what we're going to be learning about is how do we deal with situations where chemical reactions can run backwards. All right, it turns out that the vast majority of chemical reactions that we've been looking at this year actually go both directions. They go forward and backwards. Everything we've done so far has been focused on how do we take reactants and turn them into products. Last unit, we spent a lot of time talking about this reaction, the reaction of nitrogen and hydrogen to form ammonia, known as the Haber process. Okay, but this reaction, all by itself, ammonia will react and turn back into nitrogen and hydrogen. This is a thing that happens. Okay? So when you have a reaction vessel, a container, where you're trying to do this, you're trying to make fertilizer, both of these reactions are taking place at the same time. Instead of representing them as two different separate reactions, we combine these reactions and we use this fancy double arrow setup. Okay? So when you see this double arrow, and we've seen it in worksheets and problems and stuff, it's just shown up a couple of times and we've basically ignored it. It's no longer ignorable. Now we need to learn how to deal with it both conceptually and mathematically. We're going to have to go ahead and take care of it. The idea is that nitrogen and hydrogen react to produce ammonia. Ammonia reacts to produce nitrogen and hydrogen. That anytime you have a chemical system like this, both reactions keep happening. Okay? What we're interested in is when does the system, this reaction that can go forward and backwards, when does this reaction stop changing? Okay? Because while we have done a ton of stoichiometry and we've said, oh, the reactions run to completion. We use up all the reactants to produce products until we run out of something. It turns out that the vast majority of time, that is not how chemical systems work. That reactants turn into products, but then at the same time, the products start turning into reactants. That process never stops, but it does reach an balance where the amounts of products and reactants stop changing. And in fact, that is one of the critical definitions of equilibrium, the balance between the forward and the reverse reaction. One way that we can define equilibrium is by measuring the concentrations. We could, for instance, graph the concentration of nitrogen and hydrogen, our reactants that we put into a container. They start off with some initial concentrations. There are no products at the start. We did not put any ammonia into the container. Nitrogen and hydrogen react. As they react, the concentrations, the amount of hydrogen and nitrogen go down. You can see that the slope of these lines is different because there are different coefficients. We use the hydrogen up faster than the nitrogen. This was a classic question of kinetics, was one of the questions on our last test. Okay? Or on the review sheet, I should say, practice test, where it said, hey, how do the rates of these two things compare? Well, the rate of consumption of hydrogen is faster than nitrogen because the coefficient of on the hydrogen is a 3, right? So we use it up 3 times faster. That's why this line is steeper, okay? But what we're not, in this graph, focused on that rate of change. What we are interested in, one way that we can define equilibrium is the point at which the concentration stops changing. So, as the hydrogen and nitrogen decrease, the concentration of the ammonia increases. As the concentrations of nitrogen and hydrogen decrease, the rate of the forward reaction decreases. We know that rate depends on concentration. All right? That's what we just spent a good chunk of time learning about last unit, the relationship between rate and concentration. As that rate decreases, that forward reaction, how fast we're using up the reactants, slows down. As we create ammonia, the reverse reaction begins to happen. And as the concentration of ammonia increases, the rate of the reverse reaction speeds up. Eventually, we come to a place where the concentrations of all the chemicals become stable. They stop changing. Notice this doesn't mean that the chemical reactions stop. It means that the rates at which they're getting used up become equal. And that is the second way that we can define equilibrium. Okay, so the two ways to define or identify equilibrium: when the concentrations stop changing, become stable, okay? And when the rate of the forward reaction equals the rate of the reverse reaction. So notice there's two different graphs here. Both of them are time, but one of them relates concentration to time, and one of them is rate to time, okay? Here, we're looking for the graphs to become flat, to become stable, and here we want the rate to become equal. Both of those things are necessary and identifiers that we have reached a balance, that we have reached equilibrium. Question?
So, first graph, is there a reverse reaction happening?
So, at the very start, there is no reverse reaction taking place because the concentration of the ammonia is 0. But as soon as the nitrogen and hydrogen react and begin to produce ammonia, that concentration is no longer 0, and the reverse reaction starts to take place. So as that reverse reaction takes place, we start using up ammonia to produce nitrogen and hydrogen. But at the beginning, the rate of the forward reaction is much higher than the rate of the reverse reaction because the concentrations of the reactants, nitrogen and hydrogen, is much higher. Okay? But as we use it up and we convert the nitrogen and hydrogen into ammonia, the ammonia builds up, concentration of nitrogen and hydrogen decrease, the rates of the forward and the reverse reactions become equal. And that's the point at which we reach equilibrium.
How would this work with like a Fosbury reaction? Aren't they like the rate of reaction?
Sorry, say it one more time.
Like isn't like a Fosbury reaction?
I mean 0 order.
0, yes.
Yeah. So 0 order reactions are going to function a little bit differently. But what we're really focusing on is the reverse, the balance between the forward and the reverse reaction. So while a 0 order reaction, it might be not 0 order, it might be 0 order for that one. The reverse reaction will generally depend on those concentrations. Okay. So as the concentration of the reactant takes place, of course, even for a 0 order reaction, if there's no reactant, there can't be any reaction. So while it is independent, it's not a relationship, you still can't have a chemical reaction without the reactants. So, yeah, there is some balance there. There's still a way to achieve that kind of balance.
Once it reaches equilibrium, can it go back?
No, once outside of some external change. So if you take your container and you seal it up, you start out of balance, you reach balance, bam, it's done. It's going to stay in balance. But you can disturb that equilibrium. You can add something. You can change the temperature. You can change the volume. There are things you can do to disturb the equilibrium, but that's a lecture for next week. Okay? All right, so conceptually, we have this idea. that reactions start out of equilibrium and they come to equilibrium when these concentrations stop changing. All right? When the rates of the forward and the reverse reaction become equal. We want to be able to model that mathematically. We need to be able to calculate what is this balance point. Okay? And so to do that, we use something known as the law of mass action. All right? The nice thing here is that the law of mass action is simply a mathematical ratio that we derive from the balanced chemical equation. In our reaction of ammonia, the production of ammonia from nitrogen and hydrogen, we can write the law of mass action by taking the concentration of the products and using the coefficient as an exponent. And we take that products and we divide it by those same values for the reactants. So the law of mass action for this chemical equation, chemical reaction, says take the concentration, square brackets, of ammonia to the second power, coefficient is 2, and divide it by the reactants, the nitrogen to the first power, coefficient of 1, the hydrogen to the third power, coefficient of 3. So notice this is where the coefficients actually do matter. Okay? What it's describing is how the things change, the ratio inherent in the way that the values are changing. All right? Now, this law of mass action gives you a number. That number and what it represents is the ratio of the products divided by the reactant. Okay? We can look at that ratio, that number, at different points along this process of reaching equilibrium, right? At the start, because we have zero products, the value will be 0, okay? And the starting point is generally not super useful. Usually some of the values are 0, so it's either undefined or 0. In this area here, where we're not at equilibrium, we call the result of the law of mass action the reaction quotient, okay? And that is Q. Q is the reaction quotient. It is what is the ratio of the products and reactants when we are not at equilibrium or not sure if we're at equilibrium. So this ratio here changes over time as the amounts of reactants go down and the amount of products go up in this example. It doesn't have to be that. You could start with reactants. You can start with products. That's a big change now where reactions can go forward and backward. Over time, this value changes until we reach some point where these concentrations stop changing. Okay? At this point and going forward, the ratio of products divided by reactants will always be the same value, a constant, an equilibrium constant. Okay? So, once the system, what I've put into the container, has reached equilibrium, this ratio, products over reactants, equal a constant value. Right? So as long as the system is reaching equilibrium, this system at a given temperature will always equal the same ratio. What you put into the container is not going to determine where this value is. This ratio between products and reactants is determined by the rate constants. This value is actually dependent on the lowercase k rate constants for the forward and the reverse reaction. Because that ratio is going to tell you how much products and reactants do you need for the forward and the reverse reaction rates to become equal. Okay, so that's not math that we're typically going to have to do, but it is in my opinion, a really good way to think about what's happening. That the rates of the forward and reverse reaction are becoming equal. The key thing, and the thing we're going to spend a lot of time using and dealing with, is for a given chemical reaction at a given temperature, the ratio of products over reactants, everything raised to their coefficient powers, will equal a constant value, known as the equilibrium constant. You'll see it as capital K sub EQ, capital K with a sub C for concentrations. There are some variants of it that we'll learn about next week. All right? So, our law of mass action is equal to K. All right? But there are some ways that we can affect and change this. In particular, if I take this equation and I write it in a different format. So let's look at a generic version, because it doesn't have to be this chemical reaction. It could be any chemical reaction. The law of mass action is then the concentration of your products raised to their coefficients as powers equal to the K, okay? The rate constant. And this equation is on the useful equation sheet, okay? So just like this, they use slightly different letters, but it is essentially A plus B, produce C and D. They use lowercase a, lowercase b, C, and D. I prefer slightly different letters. But this generic form is there to help you remember it's products divided by reactants. All right, now here's a question. I can take this chemical reaction and I could write it, say, backwards. What if I wrote C plus D to produce A and B? Yeah, what would I have to do to what would change? It would be take the reciprocal. Okay, and what would happen to K? You take the reciprocal of K. It would be to the -1 power. Okay, so when you change the way that this is written, that changes all of the coefficients and it changes the value of K. Here's one more thought experiment. What if I took each of these coefficients and I multiplied it by 2? The reaction's still balanced, but now it's 2J, 2K, 2M, 2N. All of these now have become squared, right? 2M, 2N, 2J, 2K. What did I do to K? K squared. Changes to the exponent, changes to the coefficients, become exponential changes. So when a problem, as you will see on the worksheet, says, hey, here's one chemical reaction, we modified that chemical reaction. We flipped it around. We multiplied it by some number. What's the new equilibrium constant? You say, hey, what change did I make to the chemical equation? That change becomes an exponential change on K, on the equilibrium constant. Question? So, what you need to realize is that it's going to be K. The question is, how does K prime, the new K, relate to the old K? Right? Because it would still just be K. What you would say is, if I want to relate the old K to the new K, I take old K squared to become new K. That's the process. That's what they're going to ask you. The questions are going to say, what is the value of the equilibrium constant for this reaction written this way? And you need to recognize how you can change the original one into the new one. That's the type of problem. All right? Now, a couple of ways that we can calculate K, right? On tests and things like that, we generally don't see, hey, start from kinetics and figure out what the K value is. That's a thing that is doable, but it's not common at this level, okay? What we typically see is they will give you the concentrations. Okay, so the problems we're going to see are going to look like this. They're going to say, hey, we know the balanced chemical equation. Okay, it's printed on your lecture notes. It's the nitrogen plus 3 hydrogens to produce 2 ammonias, right? I want you to calculate based on these values. These were the concentrations found at equilibrium. So we started at some point. We don't know what it is yet. We didn't deal with a starting point. The chemical reaction took place, and we reached this equilibrium value. What is the value of K? All right, that's our first question. Step 1, write down the balanced chemical equation. It's printed on the lecture notes, but it is, right, the nitrogen gas plus 3 hydrogen gas to produce / come from 2 ammonias. Step 2, write down the equilibrium expression. That's the K equals concentrations in square brackets, like that expression, that mathematical expression. And step 3, plug in these values and solve for K. All right. So in the example box, let's do that. All right. So let's take a look. It is products over reactants. That's on the useful equation sheet. On the useful equation sheet. Make sure that you have this down. Make sure you have this down. You need to know how to take a balanced chemical equation and turn it into the equilibrium expression. With 100% certainty, the AP test will, okay, not 100%, 99.99% likely that they will, in one of the questions, ask you to write an equilibrium expression. Shows up almost every year. Okay, so this is something that we know will be on the AP test. They will ask you to write the equilibrium expression. Then you take the equilibrium expression and plug the known concentrations at equilibrium into these values. Right? So the concentration of the ammonia is 0.14. Remember that then becomes squared. The concentration of the nitrogen is 0.943. Concentration of hydrogen, 0.829. That's cubed. Then you go through and do the math. K is a dimensionless ratio. It doesn't have units. They cancel out for all intents and purposes. Okay. There are no units for K. It doesn't have units. It's a ratio. Most ratios don't have units because they cancel out. Like when we talked about the mole fraction. No units. Okay. You solve for K, you do the math. 2.42 times 10 to the negative 2, or 0.0242. Make sure that you are putting these numbers into your calculator correctly. You need to do all of this on the bottom. If you type into your calculator this number divided by this one times this one, the calculator will do this divided by that, get an answer, and then multiply by this, which is not the math you're trying to do. Use parentheses around the stuff on the bottom. Okay? Use parentheses around the stuff on the bottom. Any questions?
We did another one.
Yeah, there's a whole worksheet full of them to do. And then, after you finish the worksheet, there's an active assignment to practice. So, yes, there are lots of practice problems. Hop 2. Do the worksheet first. Do the worksheet first.